So another important type of graph, or property that a graph can have, G is called bipartite. If the set of vertices, V, can be partitioned such that no vertex in V1 is connected to another vertex in V1, and similarly for V2. So let me write that down. So no vertex in V1 is connected to another vertex in V1, and similarly for V2. So what does this mean? Let's just draw some pictures and it should be much more clear. So it is traditional to draw bipartite graphs where you draw the edges, or the vertices in V1 on one side and V2 on the other side. Or sometimes you can use a row and another row instead of columns. And then the point is that there's no edges within V1. These are not allowed. You only have edges that go from one side to the other side, like that. So this is okay, that's a very messy drawing. This is an example of a bipartite graph. But they will not always be, presented to you in this way. A graph is bipartite, basically if it is possible to draw it in this way, not necessarily if it's already drawn in this way. So the 2 cube, for example, is drawn like this. And it's not clearly bipartite in the sense that, for example, if you were to partition it like this, you can see that there's an edge on this side. Or if you were to partition it like this, you can see that there's edges on these sides. So that doesn't exactly work. But there is a way to split up the vertices so that it works like this, which is to choose the opposite corners to be the 2 sets. So let's say this is V1 in red and V2 in blue. So if you wanted to draw it in the bipartite style, you would draw both of the V1 vertices over here, and then both of the V2 vertices over here. And your connections, let's see. So it would look like this. So it's basically if you take this, maybe this edge, and you flip it around. You twist it, and then you get this graph below. So this is another example of a bipartite graph. And just to do one more example, the 6th cycle this is also a bipartite graph, although again, it may not be obvious from the start. But this one, again, we can do similarly sort of to the 2 cube or the 4 cycle, because we can just go around the cycle coloring alternate vertices blue and alternate vertices red. And you can see that no blue vertex is connected to another blue vertex, and no red vertex is connected to another red vertex. So that makes this a partition that is a witness to it being bipartite. And what do we get if we draw it in the bipartite style? Well, we have 3 vertices in each set. And let's say that we are keeping them in sort of vertical order. So these correspond like this, and these correspond like this. That's one easy way to see it. Then these two are connected, and these two are connected, and these two are connected, and these two are connected, these two are connected. All right, so we end up with this picture. Very good. So this is an example that there are many different ways to draw the same graph, and it can be, it can be important to draw it in a particular way. And this is something that we will talk more about later when we talk about planar graphs and when we talk about isomorphism of graphs. It's important in both of those contexts. So one of the reasons that bipartite graphs are important is that they are a natural context for matching problems. And matching problems are something that comes up commonly in nature. So let me say many problems can be formulated as matching problems. And what does that mean? A matching in a graph is a subset of edges satisfying the property that no two edges in the subset share a vertex. Oh, what is that word? So essentially, requiring that no two edges share a vertex means that each vertex is matched to at most one partner, and that's why it's called a matching. So also in a bipartite graph, with partition B equals B1 union B2, we can talk about a complete matching from V1 to V2 is a matching, so a complete matching from V1 to V2 is a matching where every vertex in V1 gets matched. So in general, for example, if V1 and V2 are different sizes, then you cannot hope for both every vertex in both sets to have a match. But at least if you formulate it in a one-sided way, you can always ask whether every vertex in V1 can get matched. So let's do some quick examples of this. So let's draw some bipartite graphs. Maybe it doesn't matter too much, but so a matching is a subset of edges so that no two edges share a vertex. So for example, we can take this edge that takes up these two vertices, and then this edge takes up these two vertices, and then this edge matches the last two vertices. So this is an example of a matching in this bipartite graph, and in fact, this is a complete matching because you can see that every vertex in V1, which I'm understanding to be the left-hand side, has been matched to a vertex in V2. And just to give another example, here is another bipartite graph. And let's choose matching on this guy. So this edge matches the top two vertices. This edge matches these two vertices. And let's say this edge matches the bottom two vertices. So this is a subset of the edges, and no two vertices share, or no two edges share the same vertex. So this is an example of a matching. And you can see that it is not complete because this vertex in V1 has no partner. And in fact, you can see that you could not even extend this to a complete matching because there's nothing to match this guy with except for this vertex, but that has already been matched. So we cannot add in more edges. And with a little more thought, you can see that there is no complete matching at all on this graph, because if we look at these two vertices, then the only thing that either of them can match with is this vertex, and that tells you that they can't both be matched. So in any matching, one of these two guys will be left out. And that is sort of a hint at the theorem for when you can find a complete matching, which is called Hall's marriage theorem. Marriage, just because, you know, matching is like pairing people up to get married. So a bipartite graph with this partition of the vertex set has a complete matching. Let me say from V1 to V2. If and only if the number of vertices in the neighborhood of A is greater than the number of vertices in A for any subset of V1. And what is this thing that I just wrote down? Where n of A is the neighborhood of A is set of vertices in V2 connected to a vertex in A. So let's think about what this is saying for a second. We can find a complete matching if and only if the size of the neighborhood of a subset is at least as big as the size of that subset for any subset of V1. So that's exactly ruling out the kind of thing we observed here. Here is a subset of, so this can be our subset A of V1, and this is the neighborhood of A, which is the set of all vertices in V2 that connect to a vertex in A. And you can see that a complete matching cannot exist because the size of the neighborhood is strictly less than the size of A. So that is to say that it is fairly easy to see that this is necessary because if you ever have a subset A that is strictly bigger than its neighborhood, then not all vertices in A can be matched. Simply because there's not enough things on the other side to match them to. It is not clear at all, but it is true that it is also sufficient. So this condition, this sort of simple obstruction is the only thing you need to take care of to be able to prove the existence of a perfect matching, or a complete matching. And we're not going to prove this, but it is a nice example of a situation where things go sort of somehow as well as you could expect. So there's a simple condition that you can see if this condition does not hold, then nothing can work. But it turns out that that simple condition is enough to guarantee that everything does work if you have that thing. How nice.